Thanks, Louis. And yeah, that Collins question to Chris. I don't know if that was planned, but that was a good segue to this presentation, because that's exactly what I'm talking about. How do we connect these models of vegetation change and fire? First of all, to start, even though I'm the one speaking here, I think this work involved many, many people, some of whom are on the slide. I really want to acknowledge both Catherine and Chris, because they've really been both kind of instigators for this work, recognizing why it's important to do the work, and also, really, making it happen in terms of making the resources available to do the work. Now, you may be wondering, why the heck am I doing a talk about fire and showing a photo of the Sonoran Desert where there's hardly any fuel? And really, this was the case study, I think, that instigated the first sort of instance of us connecting fire growth models and vegetation change models. And the reason is this grass that you can see in this slide. And so this is buffalo grass. It was a grass that was introduced to the Sonoran Desert from Africa. And it's spreading really well. It does really well in this ecosystem. And as you might imagine, this area that did not have a lot of fuel continuity before now does. So typically, when we look at modeling fire, and we're doing projections in SDSIM, and we covered this in my class yesterday, the idea is to look at, maybe for now, look at historic patterns and try to characterize the historic variability in something that is uncertain, like how much fire there's going to be, and sort of model incorporating that uncertainty into the future. But here we have a situation, if I go back to the previous slide, where there is no historic analog for this situation. We have no historic data for being able to do this. And so, we're starting to talk about the Anthropocene. And really, if you Google fire and Anthropocene together, you'll get tons of papers out. This one just came out on Monday in Science. And here's a direct quote talking about trying to connect predictive modeling and data for generating forecasts of what's going to happen in ecosystems. So very applicable. It's interesting. I read through some of the paper, and they didn't mention connecting, fire growth models and SDSIM, which I was a bit disappointed, because Colin's PhD supervisor is an author on this paper. So you better have a word with Marie-Josée. But so anyways, so going back to the Sonoran Desert, this is the first paper that came out, led by Catherine, where we decided to connect SDSIM with FARSITE. And so the information that goes into the SDSIM model includes your initial vegetation conditions, things like your transition pathway diagrams, things that many of you are familiar with. Also interesting to mention, there was another modeling framework connected to this, which was habitat suitability modeling work that Catherine also did to establish where can buffalo grass grow in these areas. That's a bit of an aside. But SDSIM will run for a time step, generate a fuel map that goes into FARSITE. We will provide FARSITE externally with things like elevation and weather that SDSIM doesn't necessarily care about, but FARSITE needs to know to be able to generate fires. FARSITE will generate a fire occurrence map for that time step, and then we provide that fire occurrence map back to SDSIM to actually implement the vegetation change generated by the fire. And to do this, this was kind of pre-SyncroSim package architecture being fully established. So we had sort of a pseudo package for this using Python to kind of connect the two models together. This is the conceptual state and transition sort of pathway diagram for modeling buffalo grass. I'm not going to get into a lot of the details, but the reason I want to show it, there's two reasons. One of them, we account for a couple of things. So going from left to right, the amount of buffalo grass is increasing. Interestingly, too, at the top, the buffalo grass is undetected. You can't go and do anything about buffalo grass until you actually know it's there. You actually have to integrate inventory transitions. So these models actually include inventory as an activity that happens, and whether you're successful at finding the buffalo grass when it's there or not. And then underneath, it's detected. Otherwise, they're identical. And then we incorporate at the bottom treatment of the buffalo grass. And so we needed to do some kind of classification for each level of buffalo grass cover. What is the fuel classification or fuel class that that particular vegetation cover of buffalo grass is analogous to? So we can generate the fuel map that we provide to FARSITE. For areas that were uninvaded by buffalo grass, we based it on Landfire 2016. And these are the kinds of forecasts that we were able to generate. So we're looking at two things. One of them is just invasion and land conversion by buffalo grass. So on the left side, we have a column representing current conditions. This is the Rincon Mountain District for Saguaro National Park, and then the right is the Tucson Mountain District. And then this is 30 years into the future. The middle column is without fire, and the far right column is with including fire in the system, sort of the dark brown color areas that are basically getting converted to a grass savanna instead of Sonoran desert. And then the graphs on the right, so the dashed line, again, is just a representation of the area invaded by buffalo grass. The black line is the mean area of burn, because we ran many Monte Carlo realizations, and then each colored line is a single Monte Carlo realization. So you can see that the trend is increasing in terms of both, the average area burn, but also the amount, the likelihood that you'd get really extreme fire events. And these are all scenarios that included no action. So there was a couple of other papers that have come out. One paper, the one on the left in scientific reports, looked at evaluating many of the different uncertainties, because there are a lot of uncertainties. So doing kind of factorial analyses of the different uncertainties that go into the model. And then the one on the right looked at actually implementing different management actions and scenarios. So if you're interested in this work, I recommend that you check those out. What are some of the lessons learned? So this was a really hard thing to do. So we, there are some challenges. So one of them, I think Chris already mentioned, scalability. Like, it does take a long time for these two models to shake hands, because everything has to be done on disk, right? So SDSIM puts some files on disk. It has to stop and wait while FARSITE generates the fires, and then FARSITE puts the files on disk and SDSIM has to grab them. At the time, I don't know if this is still the case, but at the time, you couldn't run more than one instance of FARSITE at the same time on a computer, so we couldn't multi-process this. So that was also a big challenge. There was some deployment challenges. So the Python environment needed to support all this is hard to get it right on a single computer. So for me to give you the model and for you to be able to run it was actually really hard on your computer. And that predated kind of the SyncroSim package API. So it was just hard to get things to connect. It was a bit tricky. And as mentioned before, sort of the model linkages. So we've gotten pretty good in SyncroSim at doing linear pipelines. When one model runs to completion, generate your burning conditions for an entire suite of Monte Carlo realizations. But sort of having one model run for one time step and wait while the other one's done, we haven't fully completed that. I'd say that's still an ongoing challenge. And then there's this concept of, it would be useful to have just a FARSITE package for SyncroSim, where you could just do FARSITE runs and an SDSIM package and maybe get them to play with each other. We're not there yet. Right now we have a base package SDSIM, and then you have to write an add-on package that extends that. This brings me to Burn P3+. I think this project that, again, spearheaded by Chris, has really helped us overcome some of those challenges. This is a package now that you can actually, go file packages in SyncroSim and download this package. I know there's with the recent SyncroSim upgrade, there is one small bug that we're going to be fixing it. So maybe don't download it today, download it next week. But it is there. And it's very similar, except now we're talking to Burn P3+, not to FARSITE. And it's a little bit, it's much simpler to do because it's within the current sort of package architecture of SyncroSim. The other nice thing about it is you could choose to use either Cell2Fire or Prometheus. And in the future, there'll be additional fire growth models that would be integrated into this process. Here's just a couple of, like, in SDSIM, as for those of you who did some of the workshops, when you add a package, it'll extend the inputs that are required. So if you're in SDSIM and you want to run Burn P3+, you really need to be able to specify 3 or 4 things. So at the very top, you need to say, where is my Burn P3+ library, where, that corresponds to this landscape? It has things like the elevation map, all of the statistical information related to weather for this landscape and ignition locations. So that's just another SyncroSim library that plays with the Burn P3 package. We had to do it this way because we couldn't have just the Burn P3 and SDSIM packages in the same library. So we just had to point to the other library. And this is something, again, I mentioned getting rid of the add-on base versus add-on architecture would help you just see all of the Burn P3 inputs right in this library. The other thing you need to specify is if there's multiple scenarios in that library, you would specify which is the scenario that represents the landscape that I'm running. In this example, there was only one scenario, so we didn't have to do that. And then you need to specify what is the transition group that I'm modeling with Burn P3 plus. And so in this case, it's pretty obvious in SDSIM, it's the fire one. And then you also need to specify what is the state attribute, and I'll get into this a little bit more detail, that characterizes the layer that SDSIM is going to give Burn P3 in terms of specifying fuel types. And so here are the fuel types that Burn P3 needs. And so the state attribute needs to provide an ID value for each simulation cell in your landscape raster that Burn P3 can interpret as a fuel type that it recognizes. And in SDSIM, all you need to do is you need to generate the fuel types. In this example, the actual fuel types were kind of the base fuel types or the fuel type potential were the state class. And then we conditionally vary the fuel type according to age. So if a particular pixel has burned within the last 2 years, in this very simple example, we said it was 101, which is non-fuel. And after 3 years of age, it goes back to its native fuel type. So this is kind of a super simple illustrative example. Obviously, the fuel dynamics could be much more complex in terms of succession in SDSIM. And here's just some example outputs where we are tracking at the top just fire events generated by Cell2Fire in a Burn P3 plus simulation. And at the bottom, we have the fuel type maps. And so you can see that the fire events when you model fire events in SDSIM not using an external fire behavior model, they tend to be more blobby. I mean, you can introduce some factors like elevation and wind direction, but they tend to be more blobby. So these are, as Chris said, more realistic fire perimeters that you would expect to see. And then you can see correspondingly, so on the landscape, this fire generated a non-fuel window in gray at the bottom. And then after 2 years, as I specified in my sort of classification of the fuels, that area goes back to its original native fuel type. So you could, again, incorporate much more complex successional dynamics with fuels, but that was just kind of the illustrative example I wanted to show. So I think a couple of the things that we have overcome with this package, one is adding the ability to really do multi-processing. So now you can have multiple Monte Carlo realizations running in parallel. I would say in terms of scalability, file I/O is still a challenge. And I think we have some thoughts about trying to get models to connect with each other more in memory if we can, although it's a little ways away, I would say. In terms of deployment, we now, as I mentioned, we have the SyncroSim package API. We also have Conda, so we can deploy environments that are required for running things like R and Python. So we don't, if I want to give you my model, you should be able to run it on your computer without having to install 1,000 different things. And then in terms of model linkages, we have, that's part of the vision going forward. Trying to integrate both linear and iterative pipelines, and then trying to, getting packages to all play in the park together rather than being in separate silos. And where am I at?